Joey joined the jump team as soon as he started about in 2013. Yeah. And quickly became one of the core developers. And so he's been involved in a lot of the big changes in jump, but today he's going to talk about a jump extension on piecewise-linear optimization.
Thanks, Miles. Yeah, so what I want to talk to you guys about today is a package that I've written over the past couple months, essentially to help you solve optimization problems that contain piecewise-linear functions in them in some form. So hopefully I don't have to motivate this too much for this audience, but we have what is called linear optimization, which is kind of a broad class of problems where you have some decision variables x. You have a way of evaluating or scoring the values for those decision variables in linear optimization as a linear response function. And you have some set of linear constraints on it as well. So this is, surprisingly powerful kind of class of problems for modeling, and we can solve them effectively. So what I want to talk about today is kind of a generalization of this, what might be called piecewise-linear optimization. So all I've done here is I've replaced our linear objective function with a function f, which is piecewise linear. So what does that mean? It essentially means that we have a mathematical description of this form. So what we do is we break down the domain of the function into some pieces, p1 through pd. And on each one of these pieces, we stipulate that the function takes a linear form. So for example, in a univariate case here, right, the domain is, let's say it's bounded interval. And so what we can do is we can break this interval, this whole domain here, down into the segment between d1 and d2, segment between d2 and d3, and the segment between d3 and d4. And on each one of these pieces, or on each one of these subintervals, the function is linear. And we have a more complex example over here. This is a two-dimensional and bivariate piecewise linear function. And essentially, the pieces here, pieces of the domain, are just these triangles that we've kind of chopped the domain up into. Now, in each one of the triangles, the function is linear, but the function changes as you pass between the triangles. So this is a kind of a class of problems that appears in kind of many different domains. It appears in economics, in operations, engineering applications. Kind of a way I like to think about it is that it's kind of a simple linear approximation for nonlinear optimization problems. So what you get out of it is maybe not something that you would write or solve as a linear programming problem, but it's still kind of, it has a very linear feel to it. Right, so what happens is when f is convex, when your piecewise linear function is convex and you're minimizing it, right, things are kind of very easy. There's this canonical transformation where you can map this function to essentially an equivalent linear programming problem where you add some variables, add some constraints, and this is kind of this is the right thing to do. Right? If your function is convex, there is one right answer. So what happens when f is non-convex? And that's when things get kind of interesting and we have to kind of build packages to model it. I just want to briefly mention that kind of stated it here, that our piecewise linear function appears in the injective, but you can just as easily consider a case where it appears in one of the constraints. Okay, so when f is non-convex, you have a non-convex piecewise linear function. One way you can think about formulating it is using mixed integer optimization. And essentially the power of mixed integer optimization is that you introduce these discrete variables, and these discrete variables allow you to encode discrete decisions in your optimization. And so the discrete decision you have when you are solving a piecewise linear optimization problem or modeling a piecewise linear function is which one of the pieces of your domain do you lie on. So we can kind of state it mathematically here. So if we have our variable x, and then we say that y is kind of the response to the function, the value of the function, we can say that this pair has to lie in this union of sets here. And so if we look at the first one, we say that if x lies in P1, then we have that essentially the y component has to be equal to the linear value of that particular piece. We go to the second set, and it just corresponds to the second piece, and so on. Right, so this is kind of a logical way of expressing essentially this piecewise linear function in our optimization problem. And there are standard techniques for modeling this type of logic, this type of disjunctive constraint in using MIP. And when you do that, you end up with something that has d auxiliary binary variables and roughly D constraints. Right, so there's kind of a standard way to do this. So is this the right way to do this? Is this the single right way to do this? And the answer is no. This is kind of almost never what you want. So there are kind of a whole host of different MIP formulations in the literature for modeling univariate functions. So the case with this x here is just lies in just the reals, right? And kind of things get even more complex when you start going into higher and higher dimensions. Right, so there's not one right answer.
What's that formulation?
We'll get to that. Yeah, so there's a whole host of different formulations. There's no right answer, and things get complicated when you go to higher dimensions. Things are complicated when you are just in the univariate case, so we want to automate this in some way. Okay, so the first thing we want to kind of talk about a little bit is what MIP formulations are there. And there's the one I want to talk about is what I call the JP formulation. So essentially the setting here is we're just going to consider a univariate function, right? So F maps R to R. And so the JP formulation, the logarithmic formulation, is particularly small and strong. And so essentially the idea here is that the formulation is built around what's called a gray code. And a gray code is a sequence of binary vectors such that when you look at adjacent pairs, so when you look at V1 and V2, for example, the difference between them is exactly 1. So exactly one of the components flips. You go from V2 to V3, exactly one of the components flips as well. Right? And so the construction, so you give me a gray code, and then I say, okay, fine, go and construct these two sets here for every one of the components of your gray code. So essentially what you're doing is, so you fix a component J, and then you look at every kind of code in the sequence, and you say, did the component J flip when you went from the previous code to the current code? And if it does satisfy some condition, you put it in this set, and if it satisfies some other condition, you put it in that set. Right? It doesn't matter so much what the form looks like. I just want to convince you that it's complicated. Right? And then what you do is you take your univariate piecewise-linear function and you express it in terms of the breakpoints and the values of the function at the breakpoints. Right? So you take your D1, D2, D3, D4, and you look at the function value at those points. And that's kind of your description of the function. Right? And you have all this information, and you can come and you can write this formulation here, and it works, and it's fast, but what do we actually need to construct it here? First, we need to understand the paper. First, we need to find the paper. We need to understand it. Then we need to construct this gray code. So you go to a second paper, go to a textbook or something. You think, all right, so what is gray code? How do I code this? Third thing is you need to construct these sets. So this is maybe the easiest part. Fourth, you need to actually find the breakpoints, which if you have a functional form, a functional description of your function is like maybe, it's not trivial, right? So none of this is impossible. You can do it. But it is non-trivial, and kind of anecdotally, this is a real barrier for practitioners. Right? So there are many people that, if they, they might have problems where you can model it this way, and they would get good answers. They might not know that you can model it this way. They do know that you can model it as piecewise linear optimization. They might not know the right formulation, and if they do know the right formulation, they might be scared off when they actually look at it. Right? And again, this is just for univariate functions. So things get even more.
Even when you send the code. So even when you send the code to
even when you send the code. And again, this is just univariate functions, so things get more complicated when you go to 2 dimensions. Right? So in the one-dimensional case, you just have intervals. Right? So if you partition the domain, you just end up with more intervals. Now, if you're in 2 dimensions, how do you partition the domain? So one approach here that we see, and the kind of the standard approach is what you do is you grid along each one of the dimensions. So for a 2-dimensional function, you grid along this x dimension, so you pick some points. You grid along the y dimension, so you pick some more points, and that gives you a kind of a grid and some sub-rectangles, and each one of the sub-rectangles you take it and you triangulate it. You chop it in half into 2 triangles. So now there's a much richer combinatorial structure. It's even harder to model with MIP. There are a bunch of formulations that you can try. Then you run into weird things where some of these formulations only work for what you might call regular triangulations, something with some kind of structural property to it. So yeah, even more complicated. So this is where the piecewise-linear opt package comes in. So the first part of the package essentially does not touch jump. This is just a representation for arbitrary multi-dimensional piecewise linear functions. And so a big piece here that I think is, something that might not be obvious if you're, I don't know, it wasn't apparent to me when I first started that this would be useful. But a lot of the times when you're trying to model a piecewise linear function, you don't really have this breakpoint description, at least naturally, which is what the formulations typically want. You have something in terms of a functional form. If you want to approximate a nonlinear function, odds are you probably just have a description of the function in terms of x squared plus 3x to the 4th or whatever, right? What we have is we have a representation for these piecewise linear functions as well as some helper constructors to actually get you this breakpoint description. The second part is a jump extension that builds mixed linear programming models for one-dimensional and two-dimensional piecewise linear functions. So I'll talk a little bit at the end about extending this to higher dimensions. But like I said, there are 10 formulations for the one-dimensional case. I have 9 for the two-dimensional case, and there's a couple more that I haven't implemented yet that will go in at some point. Okay, so what does the representation for a piecewise linear function look like? Right? So this is really just a type alias here. This univariate PWL function is just a type alias for a piecewise linear function, parametric with a 1 here, one-dimensional. So what I'm plugging in here for the arguments are 1 through 5. So this is the breakpoints along the domain, 1, 2, 3, 4, 5. And here is a vector with just the function value at the corresponding breakpoints. So what's happening? So it's getting transformed in some way. So this first element here, so this is the value at each of the breakpoints of the domain. So again, just 1, 2, 3, 4, 5. Here we have a list with the corresponding function values. And here we have kind of a description of the combinatorial structure. Right, so it's a list of lists. So the first one here, we look at it, and it's a vector with 1 and 2. So what this says is that the first piece can be described in terms of a convex combination of the first breakpoint and the second breakpoint. So 1 and 2. Second one is 2 and 3. So it's a convex combination of this guy and that guy, and so on. Right, so this is maybe not so interesting for the one-dimensional case, but we'll get to. Sorry, I thought the next slide was a two-dimensional case, but it isn't. Okay. Anyway, like I said, that we have these helper functions for kind of transforming your functional form to this breakpoint description, right? So you can just plug in a function like sine here, and what it'll do essentially is just go in and evaluate it at breakpoints. Again, maybe not as interesting for the one-dimensional case. It gets more interesting for this two-dimensional case. Right. So here we have a bivariate piecewise linear function. So what I'm passing in these 3 arguments here. The first one is the gridding along the x direction. Second argument is the gridding along the y direction. And the third is just some functional form for what the values take at particular points. Okay? So again, the first argument for the type, first field is essentially the location for each one of the breakpoints. So we have 1, 1, 2, 1, and so on until 4, 5, and 5, 5. Right? So x direction, we have 1 through 5 in the grid. Y direction, 1 through 5 also. And each one of these breakpoints, we have a function value, essentially. And now the combinatorial structure is a little bit more complex. So the first set here is 1, 6, and 2. So what this says is you look up here and you pick the first element, the 6th element, and the second element, and that gives you the breakpoints for that particular piece. So the triangle that corresponds to is 1, 1, 2, 1, and it's hidden here, but also 1, 2. So it's a triangle that kind of looks like that. And there's also a corresponding triangle that looks like that. Oh, sorry, that's number 7. And what we've recorded here is some additional metadata that describes how the triangulation was done. So you notice in particular that we're passing in here, we're just doing the gridding. So we're looking at the x direction, we're looking at the y direction. So that gives us a bunch of subrectangles, but we didn't actually say how we're going to do the triangulation. And so what we can do is actually, since we have this functional description of what we want to kind of approximate, we can try to think about how we actually want to take the triangulation. Right? So when we have a particular subrectangle, what we can do here when we do a best fit is we can evaluate the function at the center point and look at each of the 2 possible triangulations. Right? So in 2 dimensions, we can either do this, or we can do the other option. So either triangulate this way or that way. And we just pick the one that kind of best approximates in terms of the difference at this time point, which maybe is not the correct way for doing it for every type of problem, but it's a good start. So I do want to highlight this because this is something that I don't think was really possible before. So what were the MIP formulations available for the grid triangulations? So kind of the state of the art around 2014 was you could use these universal formulation approaches kind of that work for any disjunctive constraint. And what you end up with is a number of binary variables that's equal to the number of triangles. And these really kind of don't work in practice very well for larger problems. And Juan Pablo had a small formulation for kind of this very highly structured triangulation right here. Right? So you look and like it's just a very regular pattern. What you can do essentially is you do a logarithmic formulation. You do the JP formulation for the x direction. You do it for the y direction, and then you just need one additional variable for kind of choosing which triangle you lie in for each subringed rectangle. This is essentially the logic. And then in 2015, here's 2015. There's like a small formulation for a somewhat looser structure. You still have some structural requirements in the triangulation, but now you can get a formulation with 2 additional variables. And last year we came up with a formulation that works for any triangulation and needs 9 additional variables. And then a couple weeks ago we came with one that needs 6 and hasn't been implemented yet or really written down either.
But I thought we had 4.
What's that?
I thought we had 4.
Yeah. I conjecture that this is possible with 4. But anyway. So this might seem kind of, why do we really care? This is a constant term. But it actually does have a pretty appreciable effect on performance in practice, which makes sense if you think about it, right? Because if you do, let's say you do 16 pieces in the x direction, 16 pieces in the y direction, what you end up with is you need a logarithmic number for each direction. So you need 4 variables for the x direction, 4 for the y, so 8 total. Now you double it. You more than double it if you use this approach. So if you really can get it down to 1 or 2, it does make a difference computationally. And again, the reason that I mention this is because we're doing this best fit triangulation here, which is really only possible using one of these triangulations. These before, if you just have an arbitrary triangulation space, doesn't work. Okay. So we've seen how to model this in JUMP, right? So we have a representation for what a piecewise linear function looks like. How do we actually plug that into an optimization model? So we load up the package, we load up JUMP, we load up your favorite solver. We can define a variable x, so this is just standard JUMP model, or variable. And then we can construct a gridding in the x direction. Right, so we go from 0 to 2 pi and jumps at pi over 4. And then we can call this piecewise linear function, which takes as an argument the model, the variable, the argument for the function, the gridding along the domain, and then a functional form for the values of the function. Right, so this is equivalent to actually explicitly constructing this univariate piecewise linear function object using the partition of the domain and the functional form. Right, and what this returns is z, which is just a jump variable, decision variable, and we can plug that into our optimization problem in whatever form we want. So we can put this in constraint, we can put this in objective, anything. And I mentioned that there are 10 different formulations you can try at this point for modeling this, and they all have kind of different computational properties. And so, for example, you can specify you want to use the incremental formulation, which is one that works pretty well for smaller problems in this way. So you just pass a keyword argument specifying it to this piecewise linear function. So this really is kind of just this is the entirety of the user-facing kind of footprint of the package. It's a single function. If you want, you can go in and explicitly construct the piecewise linear functions, but it's kind of not necessary. Right? So really the goal is to kind of, if you don't want to think about the formulation that you're using, if you don't want to think about, you don't want to think about this, then you don't have to.
Can I just clarify the z is like a floating point value for each triangle, basically?
Yeah. So it returns a jump variable, but it's constrained in such a way that it's going to be equal to the function value of at x. Right. So whatever value x takes at a solution, z will be equal to f of x.
So z is, if you think about it, set y, z belongs to the graph of the function.
Yes. Yes. So this is a MIP formulation for the graph of the piecewise-linear. Any other questions? Right, so again, this is kind of all the user-facing part of the package. I do want to mention briefly some new research directions we've been playing around with. Essentially, these are equivalent to the open PRs I have on my package. The first one is this notion of an optimal MIP formulation for these types of constraints. So I mentioned before that this constant term that appeared actually kind of did make a difference computationally. You went from 9 to 1 depending on the structure of the triangulation. And it turns out you can actually kind of think of this as an objective function for an optimization problem to find the smallest formulation for this type of constraint, in a particular class of constraints, or formulations rather. Right, so you can define a notion of optimality, and you can actually solve that by using a MIP. So this MIP is, at least not yet, it's not very scalable, but we can solve it for some problems, and it's kind of interesting. You construct this optimal MIP formulation, and it does actually kind of seem to work optimally. When we compare it against the other formulations, it's the best performer out of the whole bunch. And this is somewhat surprising because the other formulations kind of all take advantage of this grid structure that's implicit. Right? We're doing one direction kind of separately. We're doing the second direction somewhat separately. We're kind of filling in everything in the middle afterwards. If we're solving this with an optimization problem, that's kind of not encoded in any constraints or anything, so we could end up with really weird kind of structure to it. But this is really trivial to implement in JUMP. You just solve a MIP when you're doing the model generation. And I don't know, I think that's pretty cool that you're actually when you're constructing a formulation, you are solving an optimization problem to find the best formulation for another optimization problem. Second one, which is maybe even crazier, is we came up with this relaxed notion of what a MIP formulation is. So essentially, it's two pieces. So what you do is you take your logical constraint, you embed it in this higher dimensional space by using these auxiliary integer variables. You build up an algebraic relaxation for it. Right? So you build up your relaxation. And then what you have is you have these auxiliary integer variables. If they were kind of a standard binary MIP formulation, you just pass that to a MIP solver. It uses your relaxation, and it knows how to branch and solve your problem using branching. Right? Which you can imagine, if you're not constraining it to take binary values, you just have some set-based constraint here. And then you can treat them kind of using a constraint programming-like approach. So we came up with a way to kind of embed these disjunctive constraints along this moment curve here. This is roughly a moment curve, roughly shaped like it. And you can construct an explicit algebraic representation for what this set looks like in a higher dimensional space. And then there's kind of a way of treating these control variables with kind of a custom branching scheme. So it's roughly like the standard branching that Cplex would do, but you need to implement branching callbacks and incumbent callbacks to kind of reject solutions that are not valid and kind of maybe add some inequalities from the branch. Right? So this is, again, kind of only something that I would have tried to do using JUMP because I can't even imagine trying to get this working otherwise. It was it doesn't work well in practice, at least for this particular one that we've tried. But it's kind of I don't know, I think it's kind of a cute idea. So future directions. So we have the package that works for univariate functions, for bivariate functions. So the natural next extension is to consider higher dimensional piecewise-linear functions. So kind of the representation for the function piecewise-linear functions is there, right? So that generalizes readily. The issue is actually building the MIP formulations for the object. And so there are certain ways to do that. Kind of you can use these universal approaches. It will work. It will not work well. But we have some ideas of how to extend the strong formulations we have for these higher dimensional settings. And it's really just a matter of implementation at this point. You can also think about maybe considering more complex partitions of the domain. So not just the case where you have these regular triangulations, but you have some crazier things going on. So that is also possible if there's kind of sufficient justification for putting the effort into it. And there's also these kind of connections with similar problems that we're starting to explore more often, or starting to explore going forward. So these problems are kind of similar in the sense that you're building a MIP formulation to approximate some nonlinear function, right? So, for example, a convex envelope for a bilinear or multilinear functions. You can kind of cast it in a particular light that it kind of looks pretty similar to building a univariate piecewise-linear function, or building a bivariate piecewise-linear function. Also, approximations for structured nonlinear functions like signomial programming or difference of convex programming. So those are also cases where you could imagine approximating non-convex functions with piecewise-linear functions in a particular way, plugging that into Grobier, for example, and kind of building an algorithm to actually solve these problems using piecewise-linear optimization kind of as a subproblem. So with that, I'll take any questions.
So I guess the gray encoding method, is that a way to adapt to how the branching cut is performed in those state-of-the-art solvers?
I'm writing that right now on the big board to hear that explanation.
Yeah, so the branching behavior it's kind of, in a certain sense, equivalent to a constraint branching that you might put on impose, right? So the binary variables in the formulation kind of only appear in this very nice form here. So Zj is either equal to 0, in which case all of these lambda components are equal to 0 as well, or it's equal to 1, in which case all of these lambda components are equal to 1, or equal to 0 as well. Right, so really the binary variable branching for this formulation ends up looking like a constraint branching on the lambda variables, where you fix some of them to 0, or you fix some other ones to 0. Yeah.
So if there exist other binary or integer variables in the problem where this set of formulation is only a part of the larger problem, how will that affect the efficiency of this formulation? That's the long. I had that question a long time ago.
I mean, I think.
So you mean, so you have that formulation and then there's other mixed
there are
things?
other stuff that other constraints exist in the same time.
I mean, potentially, yes, but I think that's something that's completely intractable to try to understand. Yeah, I think kind of like the general approach in MIP for when you're thinking about building strong formulations in general is just to you build a strong formulation for a subproblem, combine it with a strong formulation for a different piece of that problem. When you combine them together, it should, if you're lucky, result in a strong formulation for the combination of the two. So I think it's a similar idea.
Do you have the SOS branching too for the formulation?
Yeah, so some of the solvers also implement SOS2 branching kind of natively, right? So they actually can solve these problems without introducing binary variables, just with doing branching on the lambda values. And so the package supports those as well. And so that works with, I think Groby has a really good implementation, which works well for small univariate functions, or smallish univariate functions. So yeah, so that's kind of one of the reasons that it's maybe nice to have a package which implements all the different ones, is because there's no clear winner. For a certain regime, if you're using Groby, SOS2 is probably the way to go. If you have a larger piecewise-linear function, you probably want to use a logarithmic or one of the other new formulations we have. It depends. There's no clear winner for every class of problems.
And you can change from solver to solver, and from version to solver, or version to solver.
Okay, so has any of the solvers implement this type of formulation?
Are they behind the scenes?
Yeah, behind the scenes. When you say if I add a SOS constraint, and they will automatically convert to this type of constraint.
I don't think that. I think. I'm trying to remember when I asked them. Because Cplex had piecewise-linear functions. Groby has piecewise-linear functions. I think that what they did in Cplex was the SOS2 branching, the constraint branching, so it didn't add the variables. Groby now adds some extra things. So one of the things they do is there's a simplex algorithm for piecewise-linear objectives. So if you have piecewise-linear objectives, it runs that simplex algorithm, that actually gives you the optimal solution is the piecewise-linear function is convex, and if not, it's a very good heuristic and improves the information. So this, in some senses, sort of like comes into this discussion of giving a good formulation. It's a really good way of telling the MIP solver, I have this piecewise-linear function. But potentially, being able to tell the solver, like Ruby, this is a piecewise-linear function, allows it to build the formulation that it would want to build, but potentially run this simplex heuristic that could be better than doing the heuristic here. So there's a question there on for instance, what could, I mean, you could maybe add let's say that this package could pass metadata information down to math proc base, so it knows that this piece of the formulation came from this piecewise-linear function, and then the solver could say like, oh, I don't know what to do with it, so I'll just use the formulation because you said it was good, or oh, I'm going to use some extra information, or even, you know what, it's like, I don't like your formulation, let me add mine. What you meant by these constraints was piecewise-linear function, I'm going to do something else. But I don't think anybody does MIP formulations.
But like, if user can have the option, that would be cool.
What's that? So
if the user can have the option to choose, like, if I want to use the generic formulation.
Right, exactly. So with this, you don't have to worry about the solver, and it's like same as changing the solver in Groovy versus Cplex. Now we have a ton of them, and yeah. So one of the, I guess, it's like this one that's a very specific branching. Joey came up with a better formulation that actually does better branching in some sense. So yeah, it's like, I guess it's like somebody who was, I think it was Cart. Was it Cart? No, what's it? Somebody said something about MIP. It's like you should always try MIP. It might as well work. It might work. It just might work. So the key is having low entry barrier. It's like the logarithmic formulation usually works very well, but there's no guarantee. So if you have to read the paper to try it, then nobody tries it.
Could you go back to the slide where you've got z equals piecewise-linear blah 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 sign?
Just like a jump model.
This one?
Yeah. Okay. So with the function sign, so can you compose functions and stuff? All that you need is for it to be univariate,
Yes.
and you have to be able to evaluate it at the d points.
Mm-hmm.
Yes.
Julia has to be able to evaluate it.
Yeah, if you, where did I have this guy? Right, so for bivariate, right, so it expects that the function takes two arguments.
Right.
You can evaluate it. And also if you're doing this best fit thing where you're evaluating at the center, you could potentially, you need to evaluate it at a non-break point as well.
Okay, so basically, once it evaluates, it can sort of just forget. Once it has the points, it can just forget about it.
Yeah, so once you have a description of each of the regions in the domain and the values of those, you have a description of the function.
Okay. My only suggestion would be, rather than having like a fixed discretization, you could consider like the curvature at different points along the function and choose points closer together in the discretization.
Yeah. So the question of how you actually choose the points is a very good one. That it's definitely true.
But the method, I mean, it's just a vector of points d, right? So already you can just pick your own grid, right?
Yeah. So I think Chris's point was, if you actually want to use this to solve. Right, if you want to use this to be a good approximation for a nonlinear function, then you want to choose that in a correct way. And I think you're right, and I think there might be a way to like automate that. But
there's a few mathematical notions of curvature, like third derivative over second derivative.
Yeah, but if you just have a black box for evaluating function, then
AD.
AD.
Sure. Actually.
I think you're right. I mean, you could go and configure out what the D is, and
you can imagine writing a layer on top of this that actually does its own math as well. Yeah.
For that matter, it's not clear that you definitely want to approximate the function only considering the function. Maybe, let's say you're using this as a subroutine to solve a global optimization problem, and you solve it, and now you want to refine in some clever way that is not just, I mean, you really need to look at the optimal solution to do it.
How many of those 10 or 9 formulations are refinable? The gray code ones are not, right?
None of them.
Refinable in what sense?
Refinable in that you could add a point sort of arbitrarily between two existing points
Not
and
uniform
update.
grid.
I mean, you can add points, but you just have to reformulate it.
Right, but you couldn't use like a warm start or something from the previous.
Or let's say add constraint and variables.
I'm trying to think a little bit about how you might imagine changing the values of, right, because you have a description in terms of the breakpoints. You can imagine maybe trying to come up with an algorithm where you actually change the values of the function, the breakpoints, or change the breakpoint values, but I don't have a good answer for that.
Okay, because that would be okay, but adding points is tough with the gray codes.
No, but you can imagine having a fixed number of points and changing them if you concentrate around a region that you're actually interested in.
Right.
But adding an extra break, I mean, I don't even know. Actually, I'm not really sure how complicated it would be to add a breakpoint.
It's a good question. Yeah,
It's not
that's a good question.
Okay, let's thank Joey again.